we have this kind of bottom-up, top-down macro models. While GDP and prices are annually determined, all provide consistent framework to assess sectors, linkages, trade-off and different policies. Expertly capture the cost build-up associated price effect due to demand-supply gap, which is very much important because maybe 20 or 30, 40 years kind of period. Our problem with this kind of model is that data constraint in any country doesn't permit all possible technology choices. Also does not permit quantifiable energy needs in physical units, which are also needed at some point of view. So these kinds of things need calls for an integrated modeling approach. Basically, we have a macro model which determines our sectoral SDP prices over a long period, of 30-year period, 2015 we are solving these models. These numbers are feed into the energy model every year, which can be direct technology choices and investment numbers. These investment numbers again are fed into macro model. So this kind of group we are trying to convert and to addressing these two models are linked and try to solve what is ultimately comes. So basically the advantage is that prices are completely captured. We don't assume that unchanged prices have changes from year to year, because as more was technology, that different product technology that supply doesn't scale up grow so much, then technology, price of that technology will go up. So this kind of energy model onto this, they will assume constant prices. So this is the kind of thing we are trying to capture this. This is our new thing which have been done. And this is not many models in India have been done still now. Though in developed countries, this kind of integration model, land use, many kind of things being done, not only in India so far, to our best knowledge. So there are what kind of integrated model? We are using a top-down, multi-regional, multi-sector, macro, or CG model. We have 5 regions. Why? One is Odisha, because Odisha is a small state. You can't, whatever happens in the rest of India will affect Odisha. You can't do Odisha. So we have to make rest of India to be model in our economy. And then the rest of world also has to be there. Because what is happening in any kind of Middle East war or Ukraine war, all this impact on the India as well as the Odisha. The model is patterned up a teacher power model, which is standard global model. We are basically down to an India scale. And all major sources of electricity like solar, wind, coal, hydro, nuclear are model. And these are linked to the bottom-up message model. Message model which align with the city sector, where energy demand by both sector, agriculture, cooking, building, transport are estimated. Electric capacity and energy needs are derived, and all technology and existing emerging are explored.
Hi. Yeah, so Dr. Amarendra will be just presenting this.
I will now take it forward from this with a little background that why we are doing this integrated assessment model. I think since morning we have been listening so many things that particularly for Odisha, where a lot of natural resources are there and the economy is depending on the natural resource. So how this transition is going to work and what are the kind of impacts that the state is expected. So when we started working on it, and this is the kind of effort that we are making with NCER to see that how the economy, society and the system can work hand in hand, because there are so many things that during transition we need to handle. So one single model, it is not possible. Like the macroeconomic model, what Dr. Poet was mentioning, it is morely focused on the economic side. It has got some limitation in the technology side, but other side, like the bottom-up model, which is the mode which we have used here, the message IX model, this is also open source systems optimization model. It is more, kind of detailed into the technology. But again, this is not sufficient to understand that what is the application and the implication of different technological transition on the economy and also on the society. So we had to integrate it. So now this integration process is going on at the national level. So I am personally involved with several ministries, especially with MOFCC and the Central Electricity Authority, as well as with the Department of Economic Affairs, to develop this India transition pathway using this kind of framework. And this is an attempt, a unique attempt, which is at the subnational level to see that how the states can perform in that way. Now, two things that I also like to highlight, that this is an evolving process. Because when we are talking about net zero scenarios, morning also we have been discussing net zero application of nuclear and so on and so forth. So we also did the similar assessment at the national level, but the issue is that when the net zero issue comes in, that it cannot be fully dependent on the technology at the mitigation side. Because there is one, kind of, I would say, a misunderstanding or the lack of understanding is happening at the national level, and it gets percolated to the state level also, that net zero can also be achieved with the support of your sequestration. Now that sequestration could be the mechanical sequestration like the CCS, or it could be the natural sequestration. Like we need to take care of our natural resources because they are also a big contributor of absorber. Now if we just simply pass on the entire cost on our mitigation effort, then it is definitely it's a very huge cost. So we need to see that how our natural resources, and especially states like Odisha, we are also doing the similar exercise for Kerala. So there all the natural resources are so rich, like you have so much of forest cover, you have so much of wetlands, you have huge coastal area, the blue carbon. These are all God-gifted natural absorber which we need to take care of, and if we maintain it, we can actually mitigate a lot of effort in terms of the the mitigation effort and the corresponding cost. So that is also our next step. We are also moving into that direction to see that how that can also be integrated into the model like this, and to see that what is the net effect. So now in the net zero context, I would like to say that here we will be focusing mostly on the mitigation side, which we have done through integrating the macroeconomic model with the message IX kind of open source energy systems model in an integrated manner. Now the beauty of this integration is that because this has got a feedbacking effect, means that you are taking the input, because why we need energy, because there are economic activities, and what is happening in this model, we are not compromising on the economic prosperity of the state or for the country. So we are allowing the economy to grow at our desired level. Now morning we have been discussing that we are in the Amrit and we are expected to grow at a much faster rate compared to what we are now. So there is at least 3 times, 4 times, 10 times kind of growth that is expected to reach the desired level. Now there is a debate that what is the definition of India being a developed economy, what is the definition, whether it will be only on GDP based development or it will be on inclusive wealth. Because the moment we grow in that direction, there will be a lot of externality and we have to spend money on to mitigate the effect of that externality. I am not going into that debate. Now if it is only based on the economy, then there is a tenfold increase of the economic activity has to be there. Now that activity cannot come without energy intervention, because energy and economy is directly correlated. We haven't decoupled our economy. We have been trying so far. Only I think globally, the Japan is one country, they can still claim that they have decoupled it, because Japan's economic growth and the energy consumption growth is more or less decoupled. We haven't reached up to that level, so we have to accept that economy and energy will go hand in hand. So based on that principle, we have developed a mechanism that how the macroeconomic sectoral output can be translated into energy. As you know, basic fundamental economics, there are land level capital that goes into the production. Now if you can decouple that, the land level capital, and also you can put energy as an input, you can do that. And once you put that energy as an input factor to this, you can actually derive a coefficient that how much energy is required to produce 1 unit of steel or 1 unit of cement. So using that simple, kind of economic principle, the production function equation, we have derived that if 1 ton of coal has to, 1 ton of steel has to be produced, then what is the corresponding energy that is required? And also we have built into another function into that production, the correlation will also change based on the autonomous efficiency improvement. Today it might take 80 kilo of coal. Tomorrow it might not take 80, it might go down to 60 because of the efficiency improvement. Just illustrative number, don't go by this number specifically. So that is also built into the equation. So we have done this adjustment inside to see that how the economy can be translated into a corresponding energy, and that goes into this model to see that because this model takes energy, useful energy demand as an input or exogenously given, or the user-defined scenario, user-defined input to the model to optimize that how to achieve that demand, what is the best mix option that is available in a least cost way. So that is the basic functionality of this model that we are presenting here. So now you see that this is the CG input. What the input is going, basically it is the sectoral output growth rates converted into the energy term. So all the CG, the macroeconomic model actually provides the output in terms of the unit, physical unit, in tons, million tons or billion tons. So that gets translated into energy because this is an energy model. So if this model understands only in terms of the energy. So this goes into this as a service demand. Now what is service demand? Because this is very important for you to understand that how this integrated model is very useful for doing this kind of transition analysis. Because this service demand is different from the final demand. The service demand is basically, it indicates that what is your requirement of energy, what this actual energy is performing on in terms of economic activity. So this useful demand, useful energy demand, service demand is not all the time in energy unit. It could be in other unit. For example, like in this model, we have used this energy, useful energy demand for transport as a unit like billion passenger kilometer or ton kilometer. So that basically indicates that what is your service demand in the economy, because how many passengers has to travel, how many kilometers it has to travel, and what is the total kilometer. So this all gets multiplied and create a unit called the billion passenger kilometer or ton kilometer in terms of the freight. So these are 9 of them are in the energy unit, but this is also called the energy service demand. And these are directly linked with the economic activity. So if economy grows at 10%, suppose, because India has to grow nominally around 10% to become developed economy by 2047. So it is around 28 trillion. In our calculation, what we have given to government, it is around 28 trillion. India will become around 13,000 plus US dollar per capita income by 2047. So in that case, what is the corresponding travel demand will be corresponding cement demand, corresponding your steel demand, all gets calculated here, and then it creates the service demand. And then through because these service demands are served through different technologies, like what is happening, like you have 1,000 billion passenger kilometer of service demand. Now that 1,000 kilometer BPM can be delivered either through rail or through air or through road. Now even within road, you can again subsplit it. It could be the two-wheeler, it could be three-wheeler, it could be buses, it could be the mini buses. Then there are multiple ways of serving that. Now it is up to, and further disaggregation is that one single bus can run on diesel, it can also run on biofuel, it can also run on hydrogen, right? So again you see that how the trees are getting built in the whole system. So we are all giving this option, like one bus, suppose the bus is supposed to deliver 100 billion passenger kilometer of service to the economy. Now to achieve that 100 billion, the bus can actually use your diesel, it can also use biofuel, it can also use electricity. So depending on the cost, depending on this LCOE, levelized cost, it will determine, the model will determine, okay, and with some constraints. So we are also giving now these constraints. Where is the? Here are the constraints are. Like whether we have a renewable energy target, GHG emissions reduction target, grid connectivity, grid stabilization constraints. So there are multiple, this is just some examples. So all these constraints are put into the whole system. That okay, I have to achieve certain percentage of renewable share. then the model will go back and calculate that, okay, how much percentage I have to convert from diesel-based bus to electric buses based on the cost, so that I can meet my demand, but overall, as a system, I can deliver the whole energy in a least cost manner. So this is a pure optimization problem, linear programming optimization problem, which has got us several constraints and it optimizes linearly. Okay, so this means that that is the whole thing. Now, I have already told you that how this linking approach and the methodology, because I am spending some time to understand, because if I directly come to the results, you will not be able to understand that how these results are determined. Now, this I have already explained, like this population, number of buildings. Suppose if I take the building energy. So how this building energy is built into this system based on the population, based on the number of houses that you have, and what is your occupancy. Now, occupancy rate, and also what are the energy that is required to keep that building operational. You have, for building, what are the energies you need? You need either cooling or heating. In the summer you need to switch on your AC, so you need cooling energy, or you also need the lighting. So these are the main two energy requirements. In some cases you need the heaters, hot water, sorry. So these are also part of it. So there are like this, that to every sector has its different components of energy, like how that particular sector are putting that. So this is a very classical way of putting energy systems into the context. There is nothing new we are talking about. This part is very, very straightforward. But our contribution, what we made is that the linking the economy to this energy systems model, and what Dr. Pahit was mentioning, this is some kind of a new approach in this country. There are several other agencies are also trying to do it, and I don't want to name them, but there are some efforts still going on. But this is a kind of a unique approach that we have taken, and we found that this approach can give a improved, if not the finest result, but at least an improved result compared to just having a top-down model, economic model, or a energy systems model. So I will just explain. I think this is the linkage model that we have developed. So this is the message model we are talking about. This is the economic model, and these are the interlinkages that we are following. I have already explained to you that how the linkages are happening. Like sectoral outputs get converted into energy or input to the model, and then this model runs, and then the output finally goes in terms of the investment to the model. So when this transition, we are talking about just transition, what is happening that you are intend to incur a lot of investments, new investments, when you are transitioning from one set of technology to another set of technology. So there is a new investment is expected, like you have to invest in battery storage, you have to invest in solar, we have to invest in wind. So there is some additional expected investment that is going to come up. Now there are two parts of it. Interestingly, you also need to understand that this investment, when you are talking about that this transition is expensive, you have to understand what these expenses mean. So I will try to give you, to just demystify that this part. I think this is very important for all of you to understand. There are two parts of it. One is that capital investment, where you have to put money to build something. Build up a power plant, build up a kind of a unit, hydrogen electrolyzer or whatever. There is another component which is called OPEX, that the cost related to its operation. When you are running this, you need to buy fuel, you need to employ people to run it, you need to get a land to set up all these things. So this is also cost. Now quite often in India, we get mixed up between the investment number and the operational cost. So what happens that if we think that, oh, okay, because renewable sector is that decarbonized low carbon pathway is very expensive. That is our general idea. Ultimately what is happening, because if you add, because that is also part, the OPEX is also part of the expenses that you are incurring on a regular basis, be it your unit is running or not. That's what it is very important to do this kind of assessment to see, because this cost captures the entire cost part, capex and opex. And that shows that in certain cases, the low carbon transition, it may be overall, could be lower than the conventional pathway. Because what is happening, you are shifting from the conventional fuel use to other fuels with the higher efficiency technology. So your operational cost over the period of time is expected to go down.
Like electric vehicles.
Yes. So what is happening, your whole economy is moving from less efficient system to high efficient system. Your investment might be looking very high at the upfront, but to maintain that system over the period of time will be much lesser than today's technology mix. So when you are comparing this transition, it is very important to see the whole cost breakup, that how my cost breakup is shifting from today's cost to the future cost. So that is one very important thing, and that's what we did, that we have extracted the investment component of it and feed back into the system, to the macroeconomic model, to see that how that additional investment is going to create the economy-wide impact. Because the beauty of macro model is that because it is an integrated network, so moment there is a flow of money into the system, it starts flowing like a blood flowing through the vessels, our veins throughout the body, to see based on our requirement how that money is going to the different parts. And the moment it goes there, it starts pushing the production of the system. And it creates job, it creates some other benefits, it creates it's called the welfare, and all these things gets created. So this is the way we estimated what could be the potential economic impact or the social impact of the transition. Next. So this is the nesting it might look too complex, but this is the nesting that we have used. I think we can skip it for the time being. This is the CG sectors, 49 sectors that we have. And this is the mapping, the components map that we have created between the CG model and the energy systems model. So here in our energy model, we have 5 sectors. And there are subcategories of the sector. We have industry, we have transport, we have buildings, then cooking. So every sector has different subsectors into it. So this is the map that we have used, that how is the CG output is mapped into our energy model. Next. These are more or less the kind of snapshots of the output interpretation. I have already explained to you that how this gets converted into, yes, please next. This next. I think.
Yeah, basically in this kind of scenario, what we do is we calculate a baseline which we have run up to 2050. Then we try to some policy scenario we try to run. We have only 2 yesterday policy scenario we have done basically. Increase in the capacity of the increase energy efficiency, augmentation of renewable energy capacity. These are the 2 scenarios we have done. But basically this is a model of the Odisha economy. So this, and with so many sectors, so this model can be used for many other kind of policy analysis. But if you want of time, we are not showing those results. We have done some calculation, etc., other kind of policy, but it can be done by various, because all the tax systems is very nicely incorporated in this model. So this kind of tax policy, tax subsidy policy changes scenario can be done, developed using the model basically.
So there, can this model can cope up with our development rate? The way we are developing,
Yes.
going to
Yeah,
develop.
yeah.
So that is actually exogenous in the model. So you can
We
write
can
the
do it.
model at what rate you want to
grow.
grow. That is the beauty of this model. You can exogenously, year-wise you can mention, okay, this year I would like to grow 7%. This year I would like to grow 8%.
Then what you need, what point is this? If you 7%, what kind of energy we need? We can do this kind of scenario. What kind of investment we need?
Then the base level planning need not be disturbed. Shall not be
No,
disturbed.
but you are
Base
giving the model that what is the trajectory you want. So the model will tell you that if you want to go in this way, this is the effect.
Basically, at the present now, basically we have done, we have a scenario, we have, this is kind of baseline scenario we have assumed now, basically. Up to 2050, we expect Odisha can easily grow this kind. And this is kind of main things, real investment, real SDP growth, around 6 to 7%, will be growing more than 6% over the years and falling towards the end. This kind of growth we are assuming, and this is the kind of consumption, government consumption, private investment, CO2 emission will go quite high. And if you don't do anything as a business as usual scenario. This is the scenarios we basically compare all our policy scenarios. And these are the kind of different sectors are there, growth. More or less all are positive sectors growing, and some of these, as usual, many of the mining or all those sectors are growing.
Another important thing for this particular integrated model is that you can see that there are disaggregation of the sectors. Now, if there is a policy that is required to push particular sectors, suppose state wants to promote a sector called forestry, suppose, one example. Like I would like the state would like to grow faster in the forestry sector, output of the forestry. Now you can mention that, okay, historically or currently my sector is growing at suppose 3%, 3.5%. But I would like to grow this particular sector to 7%. You can actually do that as well.
But then we can introduce some tax or subsidy policy, basically, in our model. And see that what kind of, that 3% subsidy rate or 10% subsidy needed to achieve this kind of regional growth. We can use this model for that kind of analysis, basically. And this kind of energy demand or base price, base scenarios will come. Maximum energy demand will come in industry sectors. And agriculture is very small. Building and the transport is some other sector, basically. And this is kind of the things we have, this kind of energy collections we have done for this, details we have done for different kind of fuel sector. And
By sector and by fuel. So this is by sector.
And by fuel type, when we call waste electricity, solid hydrocarbon. Similarly, basically, other thing we have done, all those kind of basically emissions when we coming from the different sources of electricity, industry, etc. Mainly industry the main component. We have divided two axes. Mainly industry will be pink by violet color. Similarly, we have these kind of energy demand baseline and the mixed energy mix for different kind of things for the 2050 period up to. This model basically we can run up to 2070 or 200. It's very possible to run.
So it indicates that if no action is taken, if the this current system continues, then coal will still remain the major source of energy for the state. And there is a certain growth in the electricity share. You can see that the right column, the red part is the share of electricity. So it is expected to grow slightly, but
nothing much.
Not much.
This is basically.
Sorry for the interruption. Just want to know how growth rate is exogenous to this model.
Growth rate of externals, engineers.
I said growth rate is exogenous.
Which growth rate?
Economic growth rate.
No, it's engineers. Basically depends on the labor force growth, productivity growth, investment coming. We are determining growth, depend on supply chains.
So the economic growth depends on various factors, right? So you can control those factors to achieve that economic growth.
And this is kind of things, generation mix, capacity mix. Basically, everything is coal based is showing. I think energy demand again we have found that public transport demand is not much, but when we see private transport demand will be a big factor coming. Similarly, as fuel transport, public, all these basically same kind of fossil-based kind of fuel will basically work, whether it's private, public, or in free transport.
Data where you do take
Who?
data collection. Data collection.
All from the state
State.
data.
From Odisha.
Yes,
Yeah,
yes,
yeah.
we have all the data sources from the state.
Now, of course, based on the existing kind of data, we have to collections is our collection basically.
Well, the main input that went into the
All
model
these
is-
things. We are using in Odisha input table we have constructed. Consumer survey data we have used for Odisha. Basically, all Odisha basically data. Again, this is same kind of building, kind of what kind of communicating transport create energy demand various systems coming cooking urban is a bit higher compared to this. Again, we coming to industry, building, etc. What kind of energy speed we offer, and basically same concepts and not much change we found in the business as usual. If we don't do anything, it will be called the same kind of change we found over the periods in 2050. So, finally. Okay, I think, so basically this is kind of things. So basically, if we do, even if we get this kind of thing, what kind of investment will come? We come to a picture like this. The total investment will come to around 25 to 50, capture 3.3% of cumulative SDG will be captured. Maximum will come in these domestic resources kind of things. And this is kind of based, we have done two scenarios in time is short, especially in hurry because we try to do kind of scenario. One is capacity augmentation of renewable electricity. We assume that we have a potential, we have stated potential, we have a 50% of it against potential is achieved by the end of the terminal period. This is our target. Investment funding as a constant. There is one more scenario where I assume, where along with this scenario, two is assumed that 1% total productivity growth per year for all sectors is achievable. When you try to do these scenarios, first of all, problem that whether the market can take care of it. If we just the capacity or the needs, we found that market won't do it as well. If we have a reservoir kind of stage that government doesn't do anything, we are giving some incentive, that's it. But government has to be pushing too much without any incentive or tax or subsidy or to one. Problem that you may want to, Odisha government want to increase their potential because with this so many neighboring coal-based states, unless you restrict import of coal-based electricity cheap from neighboring states, those electricity will come and take your market. So you can't, so you have to restrict import of coal-based electricity from the rest of the state. And we have to give some tax and investment. What we can do, correct some kind of taxes on the coal-based electricity and put the subsidy money to the renewable electricity. That is, we try to do this. Because that's the only way you can probably increase this capacity stock without any financial constraints. Otherwise, as it is, your renewable, even if you give the facility, etc., renewable energy on pick up. And there are two ways of kind of energy sector transition. One is either you change the transition or you increase your energy efficiency. Because what we found is that increase energy efficiency is much better of opportunity. You can really reduce your energy demand and in that way you can get a lot of better. These are the two kinds of scenarios we try to do it. And this is
How much energy do you think by use of energy consumption efficiency you can reduce the demand? Have you calculated for Odisha?
no, no,
I
no.
think that we
We have
have.
done. Yeah. We will show it, I will come to it, we will show it, how much we energy saved. It is kind of growth, I mean, one thing to deal with that, unless you have increased the energy efficiency, etc., your growth will cause faster decline. If you see the scenario 2, whether energy efficiency, your growth also fall much later. And this, we kind of think this kind of our scenario 2 basically, the increase on this, we can found that lot of renewable energy sector electricity production also increases on of this case. And for one of the things that when you try to push for a lot of renewable sector only, returns to land is a problem, because land is another problem, because solar, etc., renewable need lot of land required. And that is a creator, sometimes we found that return to land increases quite high. As you said, it will go up from negative to it has gone to quite high, which is a problem. And many of these land are, what we can do is basically are forest land, etc. How we find the land. And growth we found that because we can energy efficiency plus with augmentation of this, sectors, growth, all sectors are positive growth, there is no negative sector, doesn't decline as such. But without energy efficiency, some of the sector may lose negative growth. That is one thing. Similarly, after this, we have done this kind of, we have mixed changes with energy efficiency, this kind of scenario, we found that
You can see now the change in the energy.
efficiency, that's how it changes to base basket policy. We have done all this kind of policy basket base scenario for all these 12 mix. We have done basically. And with this kind of tinkering, we can see that many of these solid hydrocarbon, the policy scenario is for industry basically. So you need some policy rules. There is the older and a great laissez-faire, whatever new classical economics said, the laissez-faire is a good thing, it doesn't work basically. And of course, at the end of this kind of we have done for we are all scales with this kind of things. We have done, but time is short because we are trying to be. At the end of the day, what is the employment implication? That is probably anybody wants to know it. So we have done this kind of employment number calculation. I think I will better since time is short. I think these are numbers that I have styled there. Anybody can distribute it. Then I think you can go to the employment. Yeah. Employment number. These are the all investment.
These are the all estimates that we have done covered in the study.
With energy efficiency, you can see that the number of investment required is much less, drastically falls. So this is that's why you need energy efficiency is very much important to consider. You can't ignore this at all. Now the employment number basically.
Thank you, sir. As Dr. Pohit and Dr. Bhattacharya has discussed, that in the baseline scenario, if we see energy consumption in Odisha will rise, including the fossil fuel consumption also in 2050, and also the per capita emission will also rise, but it can be reduced significantly if we introduce renewable energy augmentation policy, like by taxing the fossil fuel based energy and promoting renewable energy by the revenue generated from it, and also by promoting energy efficiency. And that not only will improve the sectoral growth rate, and also there will be increase in the share of renewable energy in the fuel mix. So what will be the impact on employment? Now, why do we need to discuss employment? Because this low carbon pathway that will bring in change in composition of energy, and also the energy consumption, employment absorption capacity of different sectors are different. So as the composition changes, the employment absorption will also change. So, and also when we are talking about employment implications, we should not talk about energy sector only, because energy sector is a very important sector. It provides input to many sectors. It takes input from manufacturing, services, all sectors, and it is an important input to all these manufacturing, services, agriculture, all those sectors. So we can't separately, we can't discuss employment separately for energy sector only. So, to capture this, we have defined employment here according to the proximity of the nature of employment to a particular to energy sector. So, we have defined direct employment and total employment. What is direct employment? Direct employment is basically the employment generated within energy sector because of this interventions. So, what are those direct jobs? Those are related to the core activities to the energy sector. Say, operation and maintenance of power plants. So, this is the jobs generated there are basically direct jobs. And what are the total jobs? That can also be bifurcated into two types of jobs. One is indirect job, that is basically the jobs that are generated from the sectors which provide input to the power sector. Provide supplies and support to the power sector. And all those sectors are generating employment to the households in the economy. And that are also generating some employment in the economy. So we are defining as induced sector. So this induced and indirect employment along with direct employment is called total employment in our study. So first we talk about this direct employment. Here we see in baseline scenario, this is the blue one. It is higher than policy scenario in 2050. This is why this is happening, because Odisha is a very much energy dependent economy. Here there are large sector of coal mining, power producing sector. So this employment in this sector will be affected a little bit. This direct employment, there will be reduction in, I mean not reduction, there will be less employment in policy scenario as compared to baseline scenario. But so I think, then next, next. So if we consider this, this is the total employment. So though there is less employment in direct energy sector, direct employment, but in total employment, because energy sector is linked to other sectors, so there will be more employment in policy scenario as compared to baseline scenario. Apart from these two, there is another potential of employment generation, that is from manufacturing and installation of new renewable energy plants. So, but there is also one clause that it should be produced domestically. So, back. Okay. So if we see, this will actually produce some 0.5 million kind of. This has potential of generating 0.5 million of jobs in new and for manufacturing and installation of new renewable power plants. So this we can say that because Odisha is an economy where there are heavy industries, there are mining sector, there are coal-based power generation, so it will be very difficult to achieve a low carbon pathway, but it is not impossible if we take this augmentation of renewable energy power plants, and also we promote productivity growth, we promote energy efficiency. So there will be sectoral growth, and also the employment will not also be affected. Thank you. Job. This is a net kind of
net job.
So there are in coal sector there is job loss. This is the total result. We can do the sectoral.
The job loss we can do it separately.
Thank you.
But in net job.